Good. Session is being recorded. And now let me share the screen. Share this screen here. Okay, so here we go. So we're going to talk about queuing theory. And like I said, there's many models. And today, there's many models, but we're going to go with the most fundamental and the one that's used the most. And that's single channel, single server. That's called MM1. Then we're going to MM2, MM2. We're going to go over that. But MM2, MM3, MN1, they have MG1 or different ones like that. Once you understand MM1, then it's a matter of plug and play, but the interpretation obviously is important, and that's what we want to focus on. So the interpretation, you're going to do the same basic metrics for different models, but the interpretation is the same. And what does that mean then, right? What's the interpretation? So like, for example, we have what? Average number of customers in the system. Oh, that makes sense, right? If we have a system, and remember, what is the system? What is the system? Both the waiting line and the server. Both the waiting line and the server. Okay? Average number of customers in the system. Average number of customers in the queue. All right, self-explanatory. But different equations for different models. All right, so what is this? What is all this stuff we're going to do this session and next session? This is a mathematical study of waiting lines. And this is one where if the inputs are good, man, these things give pretty accurate, forecasts, right? They really do a good job of explaining what waiting lines are all about. So let's see. So in queuing theory, a model is constructed so that the length of the waiting line and the time you're waiting in the waiting line, we can go out there and predict those. All right, and so obviously because this is operations management, this is an important topic within this class. All right, so you see there, what is a queuing system? We need arrivals, waiting for service, and leaving the service. The assumption here is that when you enter the server or the service area, nothing gets destroyed. So if 5 goes in, 5 comes out. Does that make sense? Nothing gets lost or gets damaged by the system. That's the key assumption for this MM1 system, or single channel, single server. Let me write that down. MM1 is equal to single channel, one waiting line, single server. One service facility. One waiting line, one service facility. Okay. So again, you're going to have the arrival process, the waiting line, and the server process. When we go through this, what's going to be given to you? The arrival process and the service process. In real life, as you might imagine, okay, you have to determine what that arrival rate and that service rate is. But for the purposes of our class, these are going to be given to you. These will be given to you right now. And you can take more, they have a whole subject on this in the math department. So they'll go into how you calculate the numbers that you're putting into the system. Okay. Any questions? So you need arrival, You need the arrival rate and the service rate. Arrival rate and the service rate makes this analysis work. Okay, a lot of the same graphs as last time, but what do we need in our queuing system? What the length is? Okay, generally the longer the line, the longer the wait. The number of lines and line structures. Remember, sometimes it's one going into multiple servers, or multiple going into multiple servers. What is the service time distribution? And remember, we had the queue discipline. Remember the queue discipline? First in, first out. Okay. We also had emergency room, and we also had the best customer model. Now there were official names for those. I forgot what those names were. Okay, but there were official names. But you have to know what that queue discipline is. In our case, what we study today, first in, first out. Or what did our notes call us? First come, first serve. First come, first serve. So first come, first serve is equal to first in, first out. Remember in your accounting class, and you did FIFO, LIFO, weighted average for those who took that accounting class? Same concept, same concept. FIFO and first come, first serve is the same in accounting as it is in this class. All organizations, again, this slide is a repeat. All organizations have some type of waiting line. You always have a waiting line. And remember that waiting lines are non-value added. Waiting lines are non-value added. Waiting lines do not add any value to your company. Therefore, they're something that you want to minimize. We had this one. Remember, we had two slides like this. One of them had 4 examples, and one of them had 5 examples. I'm only pulling up this one, the 5 examples, because it has that 1-800 software support. All right, and you know how those work when you call for software support. Okay, are you a student, a teacher, or a staff member? If you're a student, press 1. If you're a teacher, press 2. If you're a faculty member, press 3. And then you go out and you press 1. Are you a freshman, a sophomore, junior, or senior? And then you press. Okay. Are you male or female? Yeah. You see how the waiting line starts getting long right there? Yeah. So they want to try to go out there and minimize that. So again, you have your arrivals, the waiting line, the server, and the exit. We're studying the system. And what is the system again? The queue, the waiting line, and the service time. The waiting line and the service time. And the customer arrivals obviously have a big influence on the length of the waiting line and also the time in the waiting line. Okay, so same thing here, but this is a good chart because it consolidates a lot of the arrival process, the queue configuration, multiple lines, single line, okay, the queue discipline, first in, first out, emergency room, best customer, and whatever the service process is. Okay, same one again, same chart again. But again, the service system is the queue and the facilities. And the reason why I picked this one is because of this one here, the priority. How do you get from the waiting line to the service facility? How do you get from the waiting line to the service facility? First come, first serve. Okay. Another common one, believe it or not, is called LIFO, last in, first out. All right. And for those of you who are in computer science, okay, and you have files that need to be processed, What is that? What is that set called? Remember they call it a stack. If you're in computer science, they call it a stack. And a lot of times when the system is going to process the next job, instead of okay, so you have all these jobs. Obviously, the one at the bottom came in first, right? But how does many times the computer system process this stack? The one on top goes next. Then the next one goes next, and then other ones come in. So the first one that came in could be waiting there for a long time. And many times when you're dealing with a stack, the computer system will deal with that LIFO. Okay? And also, if you look at the handout, and I'm not going to go into it here, but if you look at the handout, I'm also going to give you programming steps in Python. So for those of you who know Python, how do you go out there and do all this stuff that we're going to do? How do you do it in Python? That's in the handout. We're not going to go over it in this class.
Can you explain the purpose of the handout and how we should use it?
The handout is something old-fashioned that I had from a long time ago, and I'm trying to transfer the handout to the PowerPoints. But I just wanted to give you the handouts also because I never did throw it away, and people did find them useful. So it's just another source. It's another source. No, if you get this PowerPoint, you're 95% through the handout. Okay, questions? But for the computer science people, and that's one change that I made. I'm a Fortran programmer, so I had all the Fortran commands. But for your computer science, the management information systems, maybe even the accounting information systems major, I have a lot of the Python commands now. Okay, so because Python is the new hot programming language. Another one here, another one here that shows it in a little bit more detail. Okay, and remember that we had the statistical distributions of the arrivals and the statistical distribution of the service. So we're going to do MM1. So that's going to assume exponential distribution, single channel, single server. But it could be MN, like in Nancy, normal distribution. Just depends. But again, we'll just do the most fundamental one. You get this, you get them all. Oh, also, most of the models that we're going to cover, and we talked about this last time, is going to be an unlimited arrival. So how many people can go into your system? Unlimited. What about in this class when you were doing the test? Was that limited or unlimited? Limited because it's only the students in this class. But what if we were going to go out there and instead of you doing a test, we went out there and we're going to sell lemonade on a hot day. Yeah, you got 48,000 students here, 48,000 students who could potentially be your customer. Basically, that's treated as unlimited. All right, so the calling population, that's where the customers come from. It can be finite or infinite. We just talked about that. Can be homogeneous or it could be heterogeneous. All right, and like in this class, it is in terms of class years. Is this class homogeneous or heterogeneous? Heterogeneous, right? We have freshmen, sophomores, juniors, seniors. You have, like the freshman writing class, the customers or the students in that class are homogeneous. They're all freshmen. Okay? And sometimes that makes a difference. The arrival process, this determines when and where customer jobs arrive into the system. And it's important, critical, to understand the arrival process on how data gets into our calculations. Okay, so we talked about this then, and when we're talking about these queuing systems, what's important? What did we say last time? Arrivals service. Arrivals service. All right, and these are going to then, these two parameters for the MM1 system, just these two parameters are going to give us a wealth of data. You're going to be amazed at just these two parameters and how much information we can derive from these parameters. We saw this before, the arrivals, the service system. The system includes both the queue and the server, the waiting line. These are arrivals waiting for a free server. And the server, remember the server are the people or machines that will go out there and provide the service. Again, same thing, the input, the waiting line of customers, the service facilities, could be a person, could be a machine, or a combination. And then finally, the priority rule, first in, FIFO, LIFO, emergency room, best customer. And there are other priority rules too, but those are the ones we want to deal with. And when we do this one, and let me write this down, right? When we do this one, what is the queue discipline? First in, first out. First in, first out. Okay, so when we talk about the queue discipline, the priority, first in, first out. We saw this one, the arrival system, the queue, the service facility, and again, what are the two parameters that we need? Arrival, service. Arrival and service. We need the parameters from the arrival and the service. Okay. So why did I choose this one? Because of the population source. So your population source could be infinite or finite. And we just gave the example of that, right? Number of servers, how many channels that you have, and what are the arrivals and service patterns? Yeah.
What does your calculation change if it's infinite or finite?
It does. It does, yeah.
I'm asking how.
Oh, how does it change? Because in an infinite, I mean, they're just coming all the time. They're just coming all the time. A lot of times at finite, there's a big line at the beginning, and then once you start serving them, and you only have a limited amount, then the waiting line, the line gets a lot shorter. With it, whereas in infinite, it could be long all the time. Just think about Disneyland. Just think about Disneyland. Some of those lines are long all the time, right? Yeah. Okay, questions? Okay, here's this screen again. And what does this screen, what's the emphasis on this screen? Those who balk and those who renege. Remember what those mean? Balking means that the line is too long and the person is not going to go in the line at all. Reneging means that a person got into the line, and said, this line's too long, I'm getting out. That's what reneging is. The arrival rate, remember in this case, is lambda. Just like Little's law. Remember I said that was confusing? Okay, so have a different perspective of what lambda is. Okay, so this is fuzzy, a little bit fuzzy, huh? Okay, and so we have again the arrival, the queue discipline, and service facility. So when we talk about the queue discipline here also, all right, what are we going to assume? Remember, I just didn't mention the third one. What are we going to assume? Patient. So the customers are always going to get in the line. They're not going to balk. And once they're in the line, they're going to stay in the line. They're not going to renege. They're not going to renege. Okay? So, and can you have, as an example, can you have in the same, like at the same Jack in the Box, at the same Jack in the Box that you go to, right? Can you have patient and reneging at the same time? Can you be forced to be patient? The answer is yes, because at Jack in the Box, you get in the line. You're going to go to the driver. You're going to go to the drive-thru, right? And once you get into the line, that's it, right? You can't back out. They have it so tight that you can't back out. You can't go to the side. None of that. But if you go to the store, you can always renege or you can always balk, right? So it just depends where you are. It could be the same Jack in the Box, and in one, everyone is they're not patient, but once they're in the line, that's it. They're hooked, and then you can have the people who are going through in the store, in the Jack in the Box, and making their purchase. All right. So the service system, again, the system has waiting, the queue, and the service system. What are some of the factors of the service system? Service time per customer, number of lines, number of service channels, number of service phases. And what does that mean? You go here, you pay, you go to this line, you go to this phase, and you get your food. Okay? We're just talking about two there, but there could be many phases when you go through your waiting line. These are the common questions. These are the common questions that they have when you're in the queue. And right here, no, I should have changed this. Right here, this should be lambda. This should be lambda. How long is the queue? Given that, how many servers are needed? What is the total cost for servers and customer lines? And how many servers are needed to minimize the total cost? We're going to look at those calculations later tonight. All right? We're going to have all these statistics, and we'll pass these out a little bit later. We'll do all these calculations a little bit later. All these different performance measurements. Okay? We have this one, arrivals, departures, service rate, the discipline. FIFO, LIFO are the most popular. FIFO, LIFO are the most popular. And again, we go out here, all right, and we have this stack. We have this stack like this. We'll just put 4 up here. We have this stack like this. And this is happening in computer science a lot. If it was first in, first out, if it was first in, first out, which one would be processed first? Which one would be served first? This one, right? But in computer science, what happens a lot of times? Just whatever's on the top. Whatever's on the top of the stack gets served first. LIFO. LIFO. Computer science people call it stack. We're going to call, and the accountants call it LIFO. Last in, first out. Okay. Here's the terminology, the queue, the arrival rate, the queue discipline, the server, and the phases. Okay, so why is queuing analysis so important? Because these capacities problems are very important in industry. And queuing and waiting time analysis is particularly important in the service industries. Large costs of waiting and lost sales due to waiting. All right? And when we talk about the discipline, you see, what do they show first? ER, which is the emergency room. Okay. We have this, the important measures of waiting line analysis. So that's coming up. That's coming up. Okay. But you can look here and read what the definitions are. Same thing. Coming up. So here we go with the single server, single line. Okay, this is the first one of many, and this is the one, you understand this one, you understand them all. They're just different equations. And what does that mean, right? Again, going back to your accounting class, remember you had different ways of doing depreciation expense? Straight line, double declining balance. Remember all those? You don't do some of your digits anymore, and you just do weighted average. Same thing here. Okay, different ways of doing depreciation, different ways of doing waiting line analysis. Remember I was looking for this slide last time? Single channel, single phase. So there's a single waiting line. They go to the dock and get unloaded. So the ships come in from the sea, they go into the waiting line, they go to the dock and get unloaded, and an empty ship exits the system. All right? So you have there MM1Q. I'll go over these definitions. All right? But let me write it up here. Lambda is the arrival rate, okay, and mu is equal to the service time or service rate. That's going to be part of our definitions too. But what kills students? Yeah, this symbol here. Yeah, this symbol here. What are they thinking? They automatically go back to their statistics class, and they think, oh, it must be an average. Okay. Remember, what is mu? Remember, that's population mean. Boy, remember in your stats class, that just got drilled through your head, right? When you were doing the Z statistic, all that type of stuff. And the stats teacher did a good job, because now you see another application of mu, and it's confusing. So think about that, okay? Remember that. It's not the mu from your statistics class. What are the assumptions in single channel, single server? Arrival are served FIFO. Arrivals are independent. So arrival number 2 is totally disconnected with arrival number 1. Arrivals are random from an infinite population. Service times are variable, and service time is faster than the arrival time. What does that mean then, right? So the service time for, let's say for one person, is 4 minutes. All right? They're arriving once every 8 minutes. If the service time was 4 minutes and they were arriving once every 3 minutes, you see how the line's going to get long on you quick? All right? So the service time has to be greater than the arrival rate. The service rate has to be greater than the arrival rate. Okay? Same thing here. Same thing. All right? FIFO, single server, single service rate. And you see right here where my cursor is. What are we looking at? The exponential distribution. Okay, same thing here. Same thing. And what's important about this slide? Remember, what is the Q discipline? They're patient. When they get in line, they're going to go through the line. No, you see there on the second bullet, no balking, no reneging. No balking, no reneging. All right? And we have here then, we want to go out there and measure Q performance. Hey, Jack, ready? So we're going to have all these calculations that we need to do. We're going to have all these calculations that we're going to need to do. All right? And there's the calculations. So he's going to pass them out. All right. So another good set of calculations for your midterm crib sheet. Another good set of calculations for your midterm crib sheet. And I have to admit, even looking at these for, oh no, that's wrong. That's wrong. Yeah. So, yeah. Is it just one? Yeah. Thank you. Okay, and I have to admit, well, MM1, I know all of these. I know all of these. Okay, but the when we get to MM2 and all those, yeah, I don't have those. I don't have those equations memorized. I don't have those equations memorized. Okay, but you see here, and you could look. All right, see this one? Average number of customers in the system. On our handout, that's L. LS is equal to L. LS on the handout is equal to L on the PowerPoint presentation. LQ, number of WS, okay, that's W on our handout. So a little bit inconsistent. That's W in our handout. Number of customers in the queue, thank you. Okay, so LQ, that's good. System utilization, that row, that's on the top of our handout. That's on the top of our handout. And the bottom, no, I'm sorry, that's at the top of our PowerPoint presentation and the bottom of our handout. And then we got more on the back here. Okay, so enough to keep us busy. Enough to keep us busy. Again, based off the arrival rate and the service rates, based off the arrival rates and the service rates, we're going to be able to do all these calculations. Boy, that looks like that's going to be a lot of fun, huh?
It's going on my spreadsheet for sure.
Yeah, yeah, yeah. And I think the crib sheet, I think, Putty, you asked this. I think the crib sheets can be electronic. Yeah, yeah.
Thank you, want me to show?
Yeah.
Got a statement over here.
Yeah. Yeah, yeah, okay.
Do you mind if we go over all these formulas, like compare what's different from the sides? I don't want.
Oh, of course we're going to go over them. Yeah, yeah,
Like auto-ride.
yeah. Okay, because if I didn't, right? If I didn't, just to answer Putty's question, this would look all Greek to you, right? This would look all Greek to you. Yeah, lambda mu, this will look Greek to you. But you know, these are Greek letters. The lambda and mu are Greek letters, right? Yeah, so it is Greek. So it is Greek. Yeah, that's pretty good. Yeah. Yeah. Yeah, I'm kind of proud of myself there. Yeah, that's pretty good, huh? Yeah. Yeah. I'm a poet and I didn't know it. I'm a poet and I didn't know it, okay? But all of this is Greek. All of this is Greek. And we're going to go out there and translate the Greek into English. Translate the Greek into English. Okay, so how about this? Obviously, we're going to do that. Well, let's take a break because I got to spend some time patting myself on the back. All right, let's take a break. Yeah. Well, probably one of the handicapped persons told me to take this. Let him take it and then after that. Yeah, so I'm not sure, I don't want to rush these things. Yeah, he's blind. But by this weekend. By this weekend. Yeah. It's probably going to be one question multiple. Yeah. No, this one I made, and I think the next one's going to be a consolidation.
Okay, so just this.
Yeah. Yeah, yeah, all problems.
No.
No.
So only for the test.
Only for the exams. Yeah, only for the exams, yeah. Thank you.
Your schedule. Maybe you go to. Oh, 7,000.
What's the worst thing they did?
There's another way, so, right? Hold.
Okay, So let's answer, I think Putty asked this question. All right, so let's do some cross-referencing. So when you look at this, this slide, this slide presentation, when you go home, we're looking at slide number 35. Slide number 35. And you see how we got it numbered up there? It's consistent with slide number 35. Okay, so let's cross-reference this with slide number 35. Okay, so the first one, average number of customers in the system, number 3, from up there.
So you're saying LS equals L on there, basically?
Yeah. Okay, you see on the handout, average time in system, WS, number 5. Number 5 on this slide. Average number of customers in the queue, number 2 on slide number 35. Average number of customers in the queue, number 5 on slide number 35.
I thought you said average time in the system is number 5.
Average time in queue.
Average number of customers in the queue.
2.
Oh, yeah, I'm sorry. Okay, I'm sorry. Okay, so average time in system is number 5. Average number of customers in the queue is number 2 on slide number 35. Average time in queue, that's number 4 from slide number 35. Average time in queue is number 4. System utilization, that's number 1 from slide number 35. Okay, that make sense? Back page. Okay, specific number of customers is number 7 on slide number 35. Number 7 on slide number 35. Okay, and probability of no wait, number 6 on slide number 35. Number 6 on slide number 35. Who has a question? Who has a question? Everyone good? Yeah.
So use the service rate and landings arrival rate.
Yeah.
So then how would that explain system utilization?
System utilization? We'll get there. Yeah. Okay, everyone good? Let's see. Did you write down what those, did anyone write down what those numbers are? So what is average number in queue? Let's see. 2. Average time in the system. 5. Average number of customers in queue. 2. No. In queue. This is 2. Average in system is 3. Average time in the queue, 4. System utilization, 1. Okay. 7 and 6. Okay, it's going to be hard for some of you to see, but here's the numbering. Here's the numbering. Everyone good? And then on the next page, 7, 6. Next page, 7, 6.
Can you read the numbers on the first page?
What's that?
Can you read down the numbers for the first page?
3, 5, 2, 4, 1.
Thank you.
3, 5, 2, 4, 1. Everyone good? All right. So like anything else, read the question closely and see what they're asking. Read the question closely and see what they're asking. All right, so let's go with the what these definitions are. So for the purposes of this class, the arrival rate and the service rates will be provided. The arrival rates and the service rates given in this class. In this class. What is the system utilization? I think that was Armand's question. What is the system utilization? Okay, so how much the system is being used. So you might go out there and you may have a service rate of 4. The arrival rate is 3. So you have lambda equal to 3, mu is equal to 4. What is the system utilization? 75%. Okay, and lambda, for the purposes of this analysis, lambda cannot be greater than 1. And you see right here, for the stability criteria, this mu has to be less than 1. Less than 1 for the system to keep working. Questions? Everyone good on this? All right, and so you see some of these equations there again, the average number in line, all right? The same equations that you have here, a little bit hard to see on this one, but the discipline, FIFO, the arrival is the Poisson distribution, and the service time is exponential. Remember, Poisson is a type of exponential distribution. There is no limit on the length of the queue. Remember we said that it was unlimited. The queue could be unlimited. Okay, and now, again, there's the lambda, there's the mu, the average number of units in the system, LS. You see that equation there? That corresponds to the first equation in our handout, number 3 on page 35. WS, average time a unit spends in the system, that's number 2. Everyone see where my finger is? That's number 5 on page 35. All right, so I think I think this page, this is this page. I just printed out this page. You have it. Okay, and same thing here. They have the average number of the system, little bit different equation, but it's going to give you the same answer. But what about the system utilization? Same exact formula. Average number of customers waiting in the queue. See where my finger is? That's number 2. Okay, average time in the system. You see where my finger is? That's number 5. Average time in the queue. You see where my finger is? That's number 4. This slide is the back page. This slide is the back page. Okay, and this one is the back page too. Same equations. Okay, same equations. All right. So let's look at some of these examples here. Let's do this one quickly. All right. So you have lambda is equal to 2. You have mu is equal to 3. What is the waiting time? And that's 2 cars arrive per hour. 3 can be serviced per hour. So what is the waiting time if it gets into the queue here? I'm going to go out here and use equation number 4. And so for this example, how did they get that 2/3 of an hour? If we have lambda is equal to 2, mu is equal to 3. So in this case then, this is going to be equal to 2. Divided by 3. 3 minus 2. Does everyone see where each of those numbers are coming from? Does that make sense? Okay, what is the utilization rate? The utilization rate is going to be equal to lambda divided by mu. So that's going to be equal to 2. Lambda is 2. Mu is equal to 3. 66%. What is the probability of no cars in the system? So we calculated what the utilization rate is. How do we calculate the probability of no cars in the system? And that's going to be equal to P0 is equal to 1 minus 2 over 3. Oh, I don't know if you can see that. I'm sorry. Behind the screen. So it's 1 minus 2/3, 1/3. There's a 1/3 chance that there are no cars in the queue. In the queue. No, I'm sorry. In the system. There's a 1/3 chance that there are no cars in the system. That's using equation number 6 here. Let's use equation number 6. Yeah, go ahead, Arnold.
Can you use the average number of customers in the system?
Yeah.
If the arrival rate is greater than the service rate, then wouldn't that give a negative number?
Yes. Remember, we showed the slide that the row. Okay. Remember, the utilization rate has to be less than 1 for these equations to work. Yeah. Yeah. So if your utilization is greater than 1, okay, which means that your arrivals are greater than your service, these equations fall apart. These equations fall apart. Okay, questions? Questions? All right. Now, me go to this slide here. Can I show two screens at the same time?
Yeah.
Can I slide this over here? Yeah. Can you see two screens? No. Okay, so left screen, we'll leave it. Let's see if right screen here. Will that one change? Oh, good, good. Okay, thank you. So let's make this bigger. And let's solve this problem. Let's solve this problem here. I think you have all the answers. I think you have all the answers. But how about this? You have all the answers, but let's go step by step so that you feel comfortable with it. So let's do it as an Excel spreadsheet. Okay, so we have the arrival rate. Uh, $25 per hour. Now, what about that service rate, right? You see that the employee can serve one customer every 2 minutes. One customer every 2 minutes. Or how many per hour?
30.
Oh. Service rate. And does everyone see how we got 30? How about this? This should be equal to 60 minutes divided by 2-minute service time per customer. 2-minute service time per customer. They can serve 30 per hour. And how about this? Let's put the symbols here, right? So if I can find the symbols. Where's that lambda? I could do mu. I want lambda. All right, tell me if you see lambda.
Search it. You know, you see that arrow where it says like the lat, whatever it's called?
Oh, are you talking about the screen? Yeah.
See what's in the.
Right here. It could be. Greek and Coptic?
Yeah.
Okay, sure. Thank you. Now again, you have all of these answers, but let's go. There's a real value of this being done step by step. All right, so let's go on here then and let's solve these, what is the average utilization, all of those. Okay, so the first one then is the system utilization. Okay, and I'm going to use the definitions that we have here. Okay, so we have system utilization. That's going to be equal to lambda divided by mu. Lambda divided by mu. So again, do good Excel programming practices, cell reference. Lambda divided by mu, 83%. Does that make sense? Questions? Okay, tell me if you see rows somewhere. You go. Okay, so the system utilization. Okay, the next one, number of customers in line. Okay, and what do we call that? LQ. LQ. All right? So the average number of customers in the queue. All right? Watch out. This formula is a little bit tricky. So if you're programming it in, watch out for this in Excel. So this is equal to lambda squared, that's in the numerator, divided by mu times mu minus lambda. And all programmed in. So do good Excel practices. Don't type in the numbers. Don't type in the numbers. I think that's right. Let me hit enter. I'm coming up with 4 and 1 6. Anyone concur?
Yeah.
Okay, thank you. Okay, next one on this, number of customers in the system. Let me just call this LS for system. This is going to be equal to 1 divided by mu minus lambda. No, number of customers in the system. That should be, I'm sorry. This should be equal to, I'm sorry, lambda divided by mu minus lambda. I'm sorry, can everyone make this change? In the numerator, it should be lambda. I put 1. But that's wrong. I come up with 5. And how about this? Let's label this too, right? So this is 4.166 customers. How many customers are in the system? 5. See how it's easy to make a mistake on these things? So be careful. What is the average waiting time in line? So this is the average time in queue. Okay, and we're going to call that WQ. And that's going to be in this, that's going to be equation number 4. It's going to be equation number 4. So this is going to be equal then to lambda divided by mu times mu minus lambda. Out your parentheses. Get the programming down cold. Lambda divided by, left parentheses, mu times left, mu minus lambda, right, right. Right, right. Everyone good? Does anyone need more time? Okay, and I'm coming average time in queue. Okay. That's hours. So how many minutes does that translate into? 10 minutes. Questions? Questions? Does anyone need to see the equations? Okay, where are we? E, thank you. Okay, what's the average time in the system? That's going to be equal to 1 divided by, left parentheses, mu minus lambda. And I think you're going to see that my style is I tend to put too many parentheses. But I'd rather have more than less. All because of all these order of operations stuff. So what's the average time in the system? 0.2. 0.2. Okay? And that's hours. And how much time are they spending in the system then? So we're going to do 0.2 times 60. About 12 minutes in the system. About 12 minutes in the system. Okay? I'm going to add another question here. But what is the probability that exactly 2 cars will be in the system? 2 cars will be in the system. Okay? So let's go to the back page, equation number 7. Let's go to the back page, equation number 7. Hey, watch out. This one is a messy one, right? So I like to break this one out into 2 pieces. So the first one I'm going to do, this is going to be equal to 1 minus left parentheses lambda divided by mu, right, times left, lambda divided by mu, right, looking at 2 cars, raised to the second power, I'll leave that up there. Watch your parentheses. Make sure you're programming that in correctly. Okay? And I'm coming up with 11.6%. 11.6%. Anyone concur?
Yeah.
Okay? Little math here then, right? Little math here. So now I'm gonna add one more question here. What's the probability of no cars in the system? All right? So you see right here the probability of n cars in the system. But on that right part where it has lambda divided by mu raised to the n power, remember if n is equal to 0, then lambda divided by mu to the 0 power by definition is equal to 1. So it's going to be 1 minus lambda divided by mu. So you can see that's how we get the equation. That's the derivation of this equation down here. All right? And to be honest, I always cheat on this, right? I don't want to go out there and program this again. All right? Because my philosophy is the more programming you do, the greater the probability of making a key punch error somewhere. So let's do this. The probability of 0 cars, and this isn't here. This isn't here. I'm just adding this question. What is the probability of 0 cars in the system? I better do it the right way. I better not show you all my lazy tricks, because that's going to be dangerous. What's the probability of 0 cars in the system? That's going to be equal to 1 minus left parentheses lambda divided by mu. Let's program it out. Let's program it out. Let's not be lazy. Being lazy is the worst thing a programmer can do. So I'm getting the probability of 0 cars in the system about 16 and 66%. Anyone concur?
Yeah.
Yeah. The other way to do this is 1 minus the utilization rate. So 1 minus the utilization rate, system utilization. You should come up with the same answer both times. Just like your debits have to be equal to your credits. Just like your debits have to be equal to your credits. Any questions? Questions? All right, so we could have just looked at the answers, but we wanted to go through the exercise of you going out there and doing this programming because the next topic, linear programming, a lot of programming. Okay, so we have this one, the answer is 0.8333, bingo, there we go. We're good. This one, the average number of customers in line, bingo. Average number of customers in the system, good. Okay, let's see, did we do that one? Average number in queue, 0.1667 hours, 10 minutes. Did I say that right? Average time in the queue, 10 minutes. Average time in the system, 2 minutes. Okay, and intuitively, does this 12 minutes, if the average time in the queue is 10 minutes, does the average time in the system of 12 minutes, does that make sense? Does that feel right? It does, right? Because we know that they can service one customer every 2 minutes. So they stand in line for 10 minutes, they get served in 2 minutes, the 10 plus 2, there's your 12. So intuitively, that feels right. Okay, what's the probability of 2 cars in the system? 0.1157. There we go. There we go. And, oh, you know this one, a probability of 0 cars? Remember, I just made up that problem. So, but I think that the answer is right because the probability of 0 cars in the system, I think that's right because we did that calculation 2 different ways. And we got the same number twice. So that should give us the warm and fuzzy feeling that the answer that we derived is correct. So it looks like this one is good. And again, we had all the answers here, but I wanted to do this on the computer. And Jack asked this question, so I will put this in our Blackboard, this spreadsheet, so that you can go back and see all of these. Okay, and once you get real good at this, then right? Okay, so 30 and 25, I remember that. Okay. We have the next problem here. All right, so we have the next problem here. I put all the equations up here. We have lambda is equal to 24, mu is equal to 40. All right, now watch this, right? We went through the hard process of programming this. Now, what do? 24. Oh, but you're wrong. Hold on. Okay, for this problem, we have lambda is equal to 24, mu is equal to 40. Everything is done for you automatically. Everything is done for you automatically. All right, so obviously, you can see that this is a very good quiz question. Very good quiz question, right? Question was coming up. I give you lambda and mu, and then you have 7 things to answer. 7 things to answer. Make this easy on the quiz. Make this easy on the quiz, right? All right, like I said, it looks intimidating initially, but once you get used to it, and you have this spreadsheet, and again, the class mom asked that we send it to everyone. Good suggestion, so I will do so. But practice. Yeah.
I have a question. Okay, so for you now, the service rate we divided by 60 to get it equal to the same units as the arrival rate.
Yeah.
So like let's say for example it was vice versa, like the arrival rate was in minutes and then the service rate was in hours. Would we like do the same type of thing?
Yeah. Or it depends. Do you want to do this in minutes or hours?
Hours.
Yeah.
Okay.
Yeah. But if it's hours, then the answer to your question is yes. Yeah. Okay. So any questions? Any questions? All right. So that's single channel, single server. Next time we're going to go into all kind of different ones. But understand this one, and you're going to be good. Okay? Thank you. And we will see you next Monday.
I have a